The most important take-home message from this exercise, exercise 7, is that there are no one-size-fits-all solutions in data science. That is to say, that a model that is appropriate for one data set might not be appropriate for a different data set, and the ways that you evaluate model fits to one data set might be inappropriate for a different data set. So, this is, in my mind, one of the most compelling reasons to understand the math underlying data science and statistics and machine learning algorithms, because the more you understand the math, the more you will be able to customize your analysis for each individual problem that you're working on. Okay, so with that in mind, you have seen two different methods for evaluating the fit of a model to data, the sum of squared errors and R squared. Now, in the previous exercise, the grid search exercise, I was very clear that you use the sum of squared errors and not the R squared. So in this exercise, you want to do the opposite. So use R squared to evaluate the fit of the model to the data instead of the sum of squared errors. Otherwise, the code is exactly the same. So coding-wise, this is a really simple exercise. But here is the challenging part. You are going to find that R squared is terrible. It's not useful at all for evaluating the fit of the model to the data. And I'm already telling you that that's what you are going to find. And the question is the question for you, and this is really the challenge of this exercise, which is, I mean, it's one of the main challenges of data science and applied mathematics. Figure out why that is. So something doesn't look good, and you have to figure out why that is. Okay, well, I show some hints in the code, and I talk about this in the comments, and obviously towards the end of this video, I will also explain why R squared is terrible, is completely useless for this particular problem. The code here for exercise 7 is literally copied and pasted from the code for exercise 6. The only difference is this line here, the model fit to data, where I am computing the R squared of the predicted data to the observed data instead of computing the sum of squared errors. Otherwise, it's all the same. I reduced the grid resolution to 20, and that's just because we don't need a high grid resolution. Okay, so let's look at the results here. Here you see, yeah, this looks terrible. It says the empirical result, the optimal model has an intercept of 0 and a slope of 0. What is going on there? That's crazy. And yeah, so this is also showing a pair of parameters that just doesn't make any sense. And we're also getting warning messages in here for division by 0. Okay, so why doesn't this approach work? Especially when the previous approach, so let me scroll back up to that, from the previous exercise, oh, that's when I changed the model. Okay, so I'll change this back to 6 and 0. So with SSE, with the sum of squared errors, the solution was almost perfect. It was really, really close match. And, this would get even closer to the true analytic optimal result if we used a higher resolution. So this looks great with sum of squared errors. And why does R squared work so poorly over here? And we get this kind of nonsensical, confusing result. Okay, so the answer comes from plotting some of the data. And in general, the answer to many challenges and confusions in anything involving data often comes from plotting. I couldn't stress that enough. You always want to plot everything. Okay, so here's the thing. When you change the slope, that really changes the predicted data. But when you change the intercept, that's only shifting on the y-axis. It doesn't actually change the relationships across the different variables. So here, this is for one specific intercept and changing the slope. So you can see, the slope is changing. The data points are different from each other. Here, this is example model predicted data, where each of these colored lines has exactly the same slope, but a different intercept. And now you see that they all look exactly the same except for this mean shift on the y-axis. And why is that the key insight? Well, that is the key insight because remember, when you're computing a correlation, a Pearson correlation, the first step you do is to mean center the data. So all of these colored lines, when you compute a correlation, they all collapse and they all become exactly the same data stream. So in fact, the intercept here is doing nothing. It's making no contribution to the r squared value. Okay, so then here I have another plot which illustrates this concept. So this is how the data, let me go back up here for a moment. This is how the predicted data look to us, right? So the black line is the observed data. All these color lines are predicted data for different pairs of parameters. But when we're computing r squared, that's not what the data look like. This is what the predicted data look like because everything gets mean centered. So here, when we pick one intercept and different slopes, we still are getting some variability. Not a huge amount of variability, but there's still some variability across the different slope parameters. But here, when we take one slope and all the different intercepts, now you can see this, it's just one line. It looks like it's only plotting one line, but in fact, we're plotting 20 different lines, but all of those lines are exactly lying on top of each other because they are just mean shifted versions of each other. Okay, so what is the conclusion here? Let me start by telling you the wrong conclusion. The wrong conclusion is that r squared is a junk, bogus, completely useless measure of model fit to data, and you should always use sum of squared errors. That is the wrong conclusion. The correct conclusion from this exercise is that you need to think carefully about how you are setting up the model to fit your data and how you are evaluating the fit of the model to the data. R squared is a great evaluation metric, and that's why we use it a lot. I use it a lot in this book. It's used a lot in the real world, but that doesn't mean that it's always the best solution. So that is something that, again, as I mentioned at the beginning of this video, if you understand the math underlying all these data science techniques, you will be able to figure this stuff out, and that is going to make you happy, just like this happiness rating here.